Hello everyone. Today we're going to be talking about curves in the complex plane. Given continuous functions x, which is a function of t, and y, which is a function of t, a curve, capital C, is the graph of the function z of t, where the real component is x of t and the imaginary part is y of t. And t varies between a and b for real numbers a and b. And typically we'll denote the curve C this way. We'll say C is equal to z, a function of t, x of t plus iy of t. And then we'll put the interval over which t is defined. We have the curve defined as being simple if it does not cross over itself. In other words, z evaluated at t1 is not equal to z evaluated at t2 if t1 and t2 are different numbers. So here we have a simple curve. But because at no point does the graph actually intersect itself. We can't say that in this second case. Right here, t is increasing, and when t equals t1, the graph hits this point, and as t increases beyond that, the graph keeps going, and it comes back, and it goes through this point again when t is equal to t2. And so right at this point, z of t1 and z of t2 are equal to each other, but t1 and t2 are different values of t. So this is not simple. A curve, C, z of t equals x of t plus iy of t, is closed if za equals zb. In other words, it's closed if the starting point and the ending point are one and the same thing. So this particular curve is closed. Now I can add a little bit more to the definition. A curve C is a simple closed curve if the beginning and end points are one and the same, and this is the only point at which z of t1 equals z of t2 where t1 is not equal to t2. So a curve is a simple closed curve if the starting point and the end point are one and the same, and this is the only place on the curve where z of t1 equals z of t2. That's not the case in this curve, is it? Here's another place. Z of t1 equals z of t2, where t1 and t2 are not equal. So this curve is closed, but not simple closed. So I've shown what a simple closed curve is not. So now I should show what a simple closed curve does look like. And we can probably guess, but I'm going to show it anyway. Now this is probably what we were all thinking. The curve is definitely closed, but it doesn't cross over itself, so to speak. It's just that the initial point and the terminating point are one and the same. So this curve is simple and it is closed. It's a simple closed curve. Let's take a look at some special parameterized curves. This is one that we should be familiar with. The parameter t typically goes from 0 to 1. And when t is 0, let's see what we have. When t is 0, the real part is just x of 0. And when t is 0, the imaginary part is y sub 0. So at t equals 0, this is the point on the graph. Now let's have t equal 1. When t equals 1, this is x1 minus x0. So the real part is just x1. When t equals 1, this is y1 minus y0. So this whole thing is just y1. So when t equals 1, real part is x1. Imaginary part is y1. And as t progresses from 0 to 1, it traces out this graph, which happens to be a line segment with endpoints x0, y0, and x1, y1. So this is one of the parameterized functions that we should add to our repertoire. And there's another one that's very common as well. This one's kind of a no-brainer. The other one, maybe not so much, but it's fairly easy to justify, so that's what we're going to do right now. Okay, let's look at another example. Z of t equals r e to the it, where r is positive, and t is anything between 0 and 2 pi. So essentially, this is the set of all points that are a distance of r from the origin. A circle of radius r centered at the origin. Now, suppose I do this. What is this? Isn't this just a translation? And with a translation, the size and shape of the region stay the same. They're just moved to a different part of the xy plane. They're moved x of naught units to the right of the origin and y sub naught units above the origin. So this is circle of radius r and center x naught, y naught. Okay. Now, r e to the it. Can't I write that as r cosine of t plus I sine of t And I'll keep this the same. Nothing has changed about the graph of the function from here to here. I'm just re-expressing this in a different way. And now what I'd like to do, I guess, is just distribute the r inside the parentheses. So I haven't changed the graph at all. And now I guess what I'm going to do is just combine the real parts and the imaginary parts. And just rearrange. And what is this? It's a circle of radius r and center x sub naught and y sub naught. So let me put this encapsulated into its own little box. And I guess technically r doesn't have to be greater than 0. So here's the parameterized version of a closed curve that goes along the perimeter of the circle of radius r and center x naught, y sub naught. And what happens when r equals 1? When r equals 1, it just boils down to this. This is a simple closed parameterized curve that follows the circumference of the circle of radius 1 centered at x naught and y naught. One parting remark, the expression of the function z equals x plus iy, where x is a function of t and y is a function of t. In other words, the expression of the function z equals x plus iy in terms of a third variable t is called a parameterization of z, and the variable t is called a parameter. In some of our exercises, we will be asked to parameterize the function in terms of a single variable t, which is why I mentioned this.